Hello, welcome to our third week of our machine learning workshop and our second week in clustering. And today we will be covering more of advanced clustering. Last week we covered k-means and h-clust with an understanding of kind of developing a PCA-based dimension reduction before that. We're going to take that on, kind of expand on that this week and apply more nonlinear versions of dimension reduction, such as TSNE and UMAP. And we're also going to be building some really cool, we're using some really cool clustering algorithms from graph-based clustering to Gaussian mixture models to our more density-based clustering models you're seeing a lot being used right now. All right, well, let's get started. First, obviously, you got to set up all your data and packages here, load a bunch of libraries. I got a bunch of libraries here today for you. So I'll give you a chance to kind of look through these on your own. Gave you a pretty good description here, so you'll be able to match it back to where it's used in the lesson. But yeah, we're starting to really pile on some packages here. And today, we'll be using a real cancer data set. This is one I got from Experiment Hub, and is a head and neck cancer data set. And I basically downloaded from Experiment Hub and just collected basically the cell types here. And then we have 2,000 cells. Also, I subset it down to 2,000 cells just for some computational speed for this workshop here, but obviously you could do more as you wish. So I have 2,000 cells, 21,000 genes. There's some pseudogenes and stuff in there as well. And then here's our cell types present, and I will tell you to focus on here. We have our cancer cells, our T cells, and our fibroblasts are our three main populations to find in our clusters here, and then also little smaller guys here. So first, the last couple of weeks we've been working with bulk data, but now we're moving on to using single cell data. And to do that, we first must normalize your data, right? So I downloaded TPM from Experiment Hub for this. And last week I told you about how you really want raw counts. That's most important for things like differential gene analysis. It's also important for clustering, but not quite so important. But you always want to get the raw counts when possible. But I just wanted to show you that there are a lot of publications out there that use TPM as well. It's not ideal, but it's not the end of the world. So that's what we're using here as our TPM, but obviously we got to pre-process this. How many times am I going to say this? All we got to do is process this data set, and by doing that, I'll show you kind of a little pipeline I built here. And I did this on purpose. It kind of goes along with Surat. It kind of follows the same line of thinking they're using, and I did that so we can compare back later if you want to use Surat. I know that's a simple way to get introduced for beginners to do single cell analysis, even if it's not 10x. So anyway, I have my SC count subset. That's just my 2,000 cells, right? My expression data. I just have my genes by sample names. And so first I'm going to normalize by the library size, right? Then I'm going to do a log transform. And then once I do that, I'm going to find my highly variable genes. And it's kind of very similar to the VST style method in Surat that we're going to use here. So I found my highly variable genes. I remove genes with zero variance, right? Because they just don't have much use for us to really find differences, right? And then I log transform that mean and variance. And then I fit a lowest curve to basically predict the log variance from the log mean. Then I finally get the expected variance, and then I standardize that, right? And then I pretty much am there. Then I'm selecting my 2,000 most highly variable genes, and the data there, and then I will by just sorting what we already did, and then now finally I've scaled and centered my data. So now we're really good. The data's centered, it's transformed, normalized, scaled, centered. It's ready for anything else we need, any other input of any algorithms. So we're set there. So since we're going to be using mainly UMAP today, I wanted to jump in and just knock out PCA in this pre-processing step as well. So if you remember from last week or the last couple of weeks, PR comp is our base R PCA package. We put in our final scaled and centered data. And now we have our PCA results, and we can look at our embeddings here with PC embed. But how many dimensions do we keep? How many PCs do we keep? Well, let's go ahead and knock that out too right away. Let's knock out, we're going to do the elbow method, and we're also going to do Horn's parallel analysis. If we look at the scree plot from the elbow plot, we see kind of a descending each point here explaining the variance, and the shade here showing the cumulative variance explained. So, the cumulative doesn't show that high, so we may need a lot of principal components to really get a number on this data, get a feel for this data. So you look at the elbow here, I kind of, trying to curve, kind of curve on the elbow. Where should it be? Should it be like 7, 10? Should it be more like 20? I don't know. Let's go to the scoreboard. Let's go to the charts. So we're going to try the find elbow point as we used last week on the percent variance and on the eigenvalues. On percent variance, we get 2. That makes no sense. Let's just not even think about that. 51, that's basically just grabbing all of them, right? Which may be how many we need. But that just seems a little much to me as well. So we're going to use the Horn's parallel analysis that we used last week. And this actually is a much more rigorous and it's more statistical method rather than just kind of looking at some curve. So if we run that Horn's, we get 25 PCs. Normally on single cell data, you're going between 20 and 50. Remember on bulk data, it's like 5 to 15. Single cell is more 20 to 50. So we're right in the middle of that. Seems pretty logical that we can go with this Horn's parallel analysis. So I feel decent about that. So let's go ahead and keep K equals 25 PCs for the rest of the workshop on our PC embedding. So let's move on to actual clustering, right? Then we have our data set ready. So last section, I mentioned we did k-means and hierarchical clustering, which are great methods. But k-means is kind of just for spherical clusters, and it's really just a quick viz. Hierarchical clustering is really great. I can't put that down at all, but it has a hard time finding small populations sometimes, especially if they're nested. And so today, we're really going to explore some new methods here, some more advanced methods that really we're seeing and being used in the literature right now. So first, we're going to try out our nonlinear dimensionality reduction. PCA was linear. So first we're going to do TSNE, then check out UMAP. And TSNE is really about finding local cancer neighborhoods. And it stands for T-distributed stochastic neighbor embedding. And you'll see why. It makes a lot of sense why that name exists, because number 1, it's stochastic, it's random, and number 2, it uses a T-distribution in the 2D plane. So really, this is just another dimensionality reduction that helps visualize this very high-dimensional data and brings it down to 2 or 3 dimensions so we can visualize it, right? TSNE is particularly good at preserving local structures. Really, samples that are similar in high-dimensional space will be close together if they're already close together in high dimensional, and they'll be close together in high dimensional and low dimensional is the point in the local means, right? It's really good at revealing clusters. It doesn't find clusters, but it's more of exploratory visualization to reveal clusters. And this is nonlinear, so it can capture more more interesting relationships in our data. It's stochastic, so it's random. So every time you run it, it's different. The parameters reset, the initialization parameters. You gotta set a seed, or you'll never see your plot again. And you can't interpret the distance. So in PCA, you can kind of interpret distances, how far things are apart, like clusters. You can't do that in TSNE. That's extremely important. It doesn't matter how far things are apart. It doesn't mean they're more different. Okay, it's really important. So let's talk a little bit about what TSNE. How do you do it? What does it even mean? What's the logic behind it? Well, really, let's just think about it. TSNE is like creating a map where neighbors in a high-dimensional space stay neighbors in 2-dimensional space, right? So what you do here is you first measure the distances between all the points, right? So basically, you set each point under a Gaussian distribution, and we use Euclidean distance based on that distribution to really find like a similarity score basically between all the points in the high dimension, really. So we really calculate these similarities in a high D space. Okay, after we've done that, we basically initialize random 2D positions. We just throw them down on the 2D, completely random, okay? And then we once again calculate the similarities in 2D space. And the way we do that is by using doing it similar to like we did in the high dimensional, but now we use instead of the Gaussian, we use a T distribution, right? T distribution is more a lower head and fatter tails, right? So it allows a more spread than a Gaussian. So once you have those two similarities, the idea is just to move the points around in 2D until the similarities match as close as they can, right? So we keep moving the high D similarities, the low D similarities till they match the high Ds. That's all you gotta do. And one important thing is all the points have to, every step change you make using TS&E, you have to move all the points at once. So that's very computationally intensive and it doesn't scale well. But really, so really when we're moving points around, as I mentioned, there's this, basically have this Kullback Leibler divergence between high D and low D. It's kind of like a probability distribution that we're trying to minimize, basically. And by doing that, we just basically preserve these neighborhood relationships from high to low. And that's really the magic behind TS&E is the preservation of local structure. And so our main parameter for TS&E is perplexity. Our perplexity is it basically controls the balance between the local and global structure by really it determines how many neighbors each point considers. So when we're creating the map, you're looking around, how many points might be in a cluster, how many points am I going to consider around me, basically. Typical values is 5 to 50, defaults around 30, and you can imagine if you have a smaller perplexity, you're only looking at a few points, so it's more local. When you have a larger, you're looking for a more broad neighborhood. So we're going to try out some different perplexities and kind of see what's going on there. And just to show you my function here, I got a loop here that's basically just looping through the different perplexities. But I want to show you the actual function here, this RTS&E right here. So we have we're actually inputting our PCA embedding. So that's interesting, right? You can put the expression matrix in here if you want. However, we've already done this reduction. We've already reduced our dimensions down to grab that signal, right? So we'd like to actually input that into our TS&E here. But we don't have to. We can use the expression matrix too. It really just matters what your pipeline is and what you're trying to get. And perplexity is just our loop through the perplexities. Theta is just a value for basically a speed accuracy trade-off. You can normally just leave that at 0.5. Don't worry too much about it. Max iterations, the amount of times it goes through to get a better result. So that's basically the function. I'll show you it again here in a minute. Fourth thing is, let's look at the effect of this perplexity parameter. It's pretty stark. You can really see the differences here. The low perplexity, right? We're looking at local structure. So we're really looking at, like imagine this cluster. We carry out this cluster. It's really broken down and spread out. Not dense at all, right? So we can really tell what's going on in this cluster. We have a lot more interesting things go on, but as we raise the perplexity up to 30, to 50 to 100, let's look at from 5 to 100, things are squished down. And we can kind of compare the local, well, not compare by distance, but we can kind of see this global structure happening because it's more zoomed out, right? But we can't see the fine detail of this. So there's your balance between local and global, and that's how you have to kind of balance your perplexity when you're doing these visualizations. Some other parameters we can look at as well are more iterations. You can get a better convergence. You can just add in iterations. You can do a different learning rate. We didn't have it up there above, but ADA is default around 200. We lowered it a little bit. That's just kind of the speed of the ability of the algorithm to make its convergence. And let's just look at some of the differences here. We see here's the default, here's more iterations. Interestingly, the more iterations seems to be giving us more local structure, and also the lower learning rate. They both seem to be giving us kind of a little bit more of a local structure. That's kind of interesting there. So it's just a kind of key for food for thought, how you can kind of adjust these parameters to get different things. And here I'll try to do kind of a summary here for you. I won't go back through them, we just talked about it, but it's kind of an easy way to kind of look at this table, kind of look at some of the defaults and what these things do, just so you don't forget. And just a reminder here, TCNA, we care about local structure and cluster separation, but the global distances and sizes of density are not preserved. So never try to interpret these. Just kind of look at the local structure, something you really can care about, right? And kind of the preservation of differences. All right, so pretty cool, right? So we that did a pretty good job of finding our clusters or visualizing differences in density at the very least, right? So let's jump on to UMAPs, our second one, and one that's really most widely is being used right now in the literature. So UMAP, if TCNA was about finding local communities, UMAP's about mapping the whole cancer landscape. So UMAP stands for Uniform Manifold Approximation and Projection. Once again, it's a nonlinear reduction method to push down in 3D to 2D, but or high D to 2D, right? It's using this it's basically doing something very similar to TSNE, but it's using manifold learning to provide a topological representation of the data, which more preserves global structure. And this helps it improve on TSNA in several ways. So UMAP is actually good at preserving both local and global at the same time. So that's an improvement, right? It can reveal clusters often better than TCNE. And another important factor is it's much faster and it scales better to higher throughput data sets, which all we're doing in the future is higher data set. It ain't going lower. It's like inflation. It ain't going lower. So we need to start working for more scalable methods. And once again, this is nonlinear. It's kind of stochastic, kind of not. People will argue that it's not, but I get different results. So I would still set a seed because even if the method's not stochastic, sometimes just the parameters of your whole setup are reset when they run an algorithm. And we talked about the global structure and stuff. So UMAP, extremely simple, or simple, it's not easy. It's extremely similar in the way it works to CCNA. There's just kind of one difference in the first initialization of the way it calculates the similarity. So UMAP basically builds its whole analysis based on a KNN graph, so KNN nearest neighbors. So the first thing you got to do in UMAP is basically, instead of using that Gaussian distribution like we did in TCNA to find the similarities, now we're using a K nearest neighbor graph, basically. We build this K nearest neighbor graph by using different sets of distributions based on your K values, and this is how we develop our similarity score. And basically, when this similarity score is calculated with these different K nearest neighbor graph-based distributions, we can lay out this kind of result over this topological space, this manifold space. And by doing that, it helps preserve this global structure better. I don't want to get too much more in the math, it'll get confusing, but just think of it as we calculate the similarity in using a KNN graph to better connect the global structure, right, on this manifold space, right? And now we have this kind of fuzzy topological representation of these neighborhoods. So it's kind of similar. We just got a more complicated similarity score. Now we throw them down in 2D again. We can do it two ways. We can do it random, that's great, or we can use Laplacian spectral positioning, and that just kind of preserves the distances a little bit better, but you can go either way. And then once you're in the 2D, it's the same thing pretty much exactly, very similar to TSNE. It uses the T distribution to spread out and find similarity. But one interesting fact is it moves one point at a time. It doesn't move all the points at once like TSNE. So if you move one point at a time, you can scale a lot better and get much more speed. So that's another advantage. And once again, it's just, instead of doing the KL function, its subjective function is minimizing cross entropy between the high D and low D. So it's another difference there. But otherwise this key insight, once again, comes from that topological foundation of the ability to preserve this global structures as well. All right, let's get into the algorithm. There are two main parameters for UMAP, in neighbors, nearest neighbors, and min distance. So in number of neighbors, it just controls, basically, once again, kind of like perplexity, it balances local versus global structure, and it's just talking about how many neighbors do I want to focus on. It's kind of similar to the input for GCDA for that. And then minimum distance, one more thing we can do is it controls how tightly UMAP packs points together. So in your low dimensional space, right, when your things are thrown down there, your samples are thrown down into 2D, and then they're put into clusters, how dense do you want those to be, right? And that kind of really can affect your resolution of what you're seeing there. So those are your main parameters, and we're going to run through kind of a grid search here and try a bunch of the different parameters out, and I will show you the UMAP function here in a minute, but here's kind of the effects we see. And let's look at nearest neighbors first. If we go from nearest neighbors 5 to 30, it squishes it down a little bit, right? Just kind of like TCD, it squishes it down. So you're seeing more global structure now. You're losing that local structure. And minimum distance from 1 to 3, kind of the opposite, right? We see bigger clusters going this way. So it makes sense because the smaller minimum distance would mean you want smaller, tighter, dense clusters. So you can see how in that way you could balance the local and global structure depending on what you want to look at there. So let's also look at the distance parameter. So UMAP has a distance parameter. It could actually change it. Remember TCD uses the just the Euclidean, but when calculating the similarity score under the Gaussian, and we're calculating the similarity score under our K distributions, we can use Euclidean, or we can also use correlation or cosine. And I can also use an example here to kind of go through things here. It's a good point. So for UMAP, we're using the UWatt version of UMAP. So call UWatt when you're using UMAP. Here's number of neighbors, minimum distance, number of components. That's the metric. Initialization, it can be random if you leave it alone, or you can add in spectral for the Laplacian. And these guys, don't worry too much about them. They're just the default values. And for here, we're trying the different numbers here. We're trying Euclidean, different metrics here for distance. And we see here, I'm looking at the silhouette scores, the cluster stability. And I'm seeing very similar between these two, but I'm seeing cosine being the best. And that makes sense because cosine is often used for UMAP and single cell data. So cosine might be the parameter much better to go with. And just kind of a reminder of UMAP, basically, we have a mix of local and global structure. It's better than TCD for global relationships. And one interesting thing is the cluster connectivity. Since it holds the structure better, distances actually are somewhat meaningful in UMAP. So if you have a bridge between two clusters, that can indicate some kind of relationship between the clusters or a transitional state. And close clusters in UMAP are likely more biologically related than ones far away. So having these kind of bridges are to understand the differences in far away. You bring in more of the biological interpretation to these visualizations that you don't have in TCD. But you still need to use some caution. They're not perfect, right? But it's just to kind of see that as the kind of the advantage over UMAP. So now we've done that, let's just do a comparison of the two. I just did kind of a final version based on what we talked about, and let's look at what they look like. And there's our TSNE and our UMAP, and you can actually make a UMAP look exactly like a TSNE by changing the parameters. And you can also make a TSNE look like a lot of silly things by changing the parameters. So you don't want to go, but usually you can make there's a logical reason for the parameters for where they should be, right? There's nothing wrong with changing the UMAP that way, but you lose the advantage of the global structure by doing that. You can see the clusters are much more revealed, and we see global structure better. So to me, the UMAP is much better here, but whatever you want, right? To each its own. When you see here, we have 9 cell types: 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are our cancer. These are our fibroblasts, right? These are our T cells, right? These are our big populations we care about catching. And then we have some tiny ones here. They're going to be hard to catch. And we're going to see what they are. And it's also going to be hard not to find these as separate clusters. And really, are they separate clusters? There's a difference between finding the clusters and finding the cell types. This cell type, this fibroblast, could have 2 different types of fibroblast, or they could be different states of fibroblast, right? Different cell states. So just because you might overcluster, these probably should be in 2 different clusters. And later you can come in and find the cell type. So don't feel like today if you missed the cell types, you're wrong. It's more about finding the clusters, right? So let's jump into actually the real clustering now that we have the actual visualizations. At first, we'll look at graph-based clustering. It's extremely popular right now. And we basically people are using Leighton, as Leighton is the one everyone's using with Surat. And but one thing we need to do is build the graph. So these guys take actually a k-name graph as input. So we actually have to build that first. But what is that? What does that even mean? What is a k-name graph? Well, k nearest neighbors, right? We pick the k nearest neighbors we care about. Nodes are the cells, edges are the connections in the cells. These connections normally have weights based on different things. And why do we need to build this graph? Well, Leighton and Leighton, they work by finding these communities in networks, right? So if they need to find a community in a network, they need a network to start with. That's simple as that. So we need to build this graph. And by doing this, it also reduces complexity to allow you to focus on local relationships rather than these just kind of pairwise distances. Because you have more of the connection, right? Not just these crazy random distances. Not random, but you know what I mean. And you can actually capture this manifold structure within the k-name graph, as we got to do in UMAP. So that kind of keeps things on the same biological trajectory together and allows for community detection in these algorithms. And I won't go too much into how these work, but you guys know, you do pairwise distances, you find your k nearest neighbors, and you build your graph. And one thing to know is important, if you have two smaller values, you can imagine you have smaller clusters that can be a little disconnected and split. If you have two larger k, you could overconnect the graph. You might just have a couple really big clusters that really shouldn't be clusters. So, start with 20 to 30 and just try out different values. You can use elbow plots, things like that. A lot of times, just trying different things out and looking at the results will help you out. All right, so one thing is important about building the cell graph is you need to work in PCA space. You don't want to put the expression matrix in. You don't want to put the UMAP embedding in. You want to put the PCA embedding in here. And I'll show you how to build it here, the easy way and the hard way. Here we're going to pull in k nearest neighbors. So it's going to say we're going to build a k nearest neighbor graph, and we're going to use a distance matrix based on our PCA coordinates. And we're basically going to, for each cell, we're going to find its k nearest neighbors, and we're going to make a SNN. We're going to say k and SNN distributions, and from that, kind of a little bit complicated, but we're going to basically turn this into an iGraph object with this graph from our agency matrix function. So we've kind of made this agency matrix and pulled out the cell graph. And I won't go too much into it. And we also want to make it unidirectional. So we don't want the graph, we want it all to be one direction, not loop back around to itself, which can be useful in things like neural nets, but not useful here at all. And so it's kind of the hard way to make it. And here's the easy way, the quick way. Just here, you can use this ran function and call on just the PCA chords, k equals 12, and then just run this function here. We're basically just grabbing the result here into our cell graph. So that's the really easy way to do it. There's lots of ways to make a cell graph, and that's why I kind of just wanted to show you there's two ways here. I show another way to make it later on in the practice, but just know there's many ways to do it, and also some have edges, some have weights, some don't. So just kind of be aware of that. And we basically built this huge network with 55,000 edges connecting. And let's just kind of visualize this really quick. Here's 200 cells, a very small subset, or 1/10 of the data. And you can see how this graph is kind of built up here. We already kind of have some connectivity and idea of what clusters should be. So you have a basis of the community to give the algorithm. All right, so let's jump in and talk about Leighton first. And just think about, we're looking at these communities, right? Finding these cancer communities in network space. So first we want to build the KNN and then work on, see how these are connected. Leighton's really good at, it's very efficient for large networks, so it's good, it scales well. It can find fine-grained resolutions, and it works by optimizing this modularity. So it has a modularity function that basically allows clusters to find the maximum internal connections while minimizing the external connections, right? And this just gives an idea of how well the communities are structured, and this is a good score to tell you how well the algorithm is working. And this is also stochastic, so you have to set a seed, and we'll talk a little bit about resolution here in a minute. It really sets how fine-grained you want, and this is widely used in single cell, a standard method you see in Surat. Okay, so how does Leighton work? Just super simple. Let's say kind of an analogy, like it's like forming neighborhoods in a city. Like think about New York City, where you have the different boroughs, right? And you have Brooklyn, you have Manhattan. Well, most of the interaction between people happen within those neighborhoods, right? Rather than between the neighborhoods. So we really want to, so if we could build a K&N graph first to kind of connect these nearby houses and then expand the graph over to this manifold space and have a good understanding of this, of kind of this network-based connection of everything in the space, right? And then once we do that, we start with each house in its own cluster. And then we try to merge it with different points. And if by merging, we get a better manifold score, then we keep that cluster together. We do that for every single point, and we just reiteratively do that and keep trying to match things until the modularity scores level off and they don't get any better, right? And then once you do that, you kind of have these superclusters. And then the last thing you want to do is try to merge those superclusters the same way. Just try them all out, see if the modularity is better. If it's not, you say the same. That's basically all it is. And that enables you to build, just keep, repeat until you stop this optimization, and then you have, you maximize this modularity score. And then basically that modularity compares over what would you expect by random chance. So, connected to that, like I just mentioned, the thing just goes on and on and on. It has this hierarchical greedy approach, so it's repeatedly optimizing these things. So really, really greedy approach, looking for every possible different combination. So that really helps it get the right answer. So the key parameters are resolution and weights. Resolution is really the main one. The weights is just a numeric vector of the weights from the cell graph, where E equals edge. If you look below here, if you put in weights, all I did was look at the cell graph weights and called the edges here for the weights. If you don't put anything in here, it weights everything equally. And it just kind of matters how you build your graph, if you need to put that in there or not. That's a little bit minor parameter. Resolution is the major parameter, and this controls the size and number of clusters. Where you have a lower resolution, gives you larger clusters, and a higher resolution gives you more smaller clusters, right? So you have that, once again, that balance between fine grain and broad clustering. So we can run this pretty easy. I'm calling it off the iGraph function, and it's just cluster Louvain. We put in the cell graph, we put in the weights, we put it on a resolution up at 0.4 here, and this is on the lower side here, and so I'm trying not to overcluster, and then I kind of found the ones here with my highest modularity, and then I have my clusters, and then I basically look at my membership of the clusters to get my actual labels for my clusters. And we see here we found 9 clusters with a modularity score of 0.89, which is a pretty decent score. And let's just kind of look over this. This is our true cell types, our 9 clusters, and look at our Louvain clusters. It's really not that bad. We kind of overclustered there, overclustered here. But remember, these are all one cluster, all cell type, but they're different clusters, really. I mean, are these really wrong? Is it really making it wrong? Not really. The good news is that finding these different things, right? It's pulling them out and separating them. That's what's important. But it's missing the finer details. Like we're missing that. We're not connecting. We miss that and that. It's saying they're part of that. So we have this kind of, we're not doing great, but we're getting close. So we feel good about that. And here, if you want to go here, look at some of the interpretation here, and look at pull out some of the different metrics here. That's kind of gave you a quick way of doing that. Looking at the modularity, the cluster memberships, the different sizes, things like that. All right, so let's move on to Leighton now. So Leighton's just basically an improvement. It's an improvement over Louvain, and it just improves this cancer community connection. And it basically decided to fix problems where Louvain can sometimes create poorly connected or even disconnected clusters. So basically, Leighton does this by putting in a different step. This is called this refinement phase, right? And it just adds an extra step to improve cluster quality before aggregation. And it basically guarantees connectivity, that all clusters are guaranteed to be well connected. So sometimes I think what happens with Louvain is when it's merging, it pulls along little disconnected pieces with it. And Leighton's basically coming in and just making a stop to that and not allowing that. And it works on the K&N graphs like before, and it's increasingly being used more than Louvain, and especially in Surat. And the resolution is what matters, right? And that's going to be the parameter to control. And this also optimizes the same modularity. And this is extremely similar to Louvain. It only has one different step. So let's think again. Let's think about social clubs this time, right? Or the neighborhoods away. We used neighborhoods last time. Either way, the point is you build your K&N graph, right? And then you start with every point alone, and then you start merging, trying all the different combinations, and you choose you define you keep making clusters if the modularity score is getting better, right? Just like Louvain, no difference. All right. So here we go. Here's the next step here. So this is just a local moving, just like before, right? So what do we do now? What's different? Well, now we split. So once we form one of those clusters, right? Those initial communities, and we have all those, right? And we're ready to do that second step, the super aggregation, right? Well, before we do that, we take our individual clusters that have been made and we split them up randomly into tiny little subclusters. And then we check those subclusters and check to see how well they're connected by modularity. And if they are not well connected, we rethink our choices. And we may move around to different areas within that same cluster or even other clusters to try to reset things up to where the idea is if we break up a cluster to little subcells, sub-communities, they need to all be stable for us to believe that entire cluster is stable. So that's how that kind of works. And it just keeps working and moving around that greedy approach till it finds that structure. And then once you do that, you still have that last step, right? That supercluster network aggregation, right? To build those, to see if those superclusters go together, and then you have your answer. So it's really exactly the same as Louvain. You just add that one refinement step where you split those clusters halfway and just make sure they're connected well. And this really helps out, and you won't have these fake communities that are barely connected, right? And this just gives you a much more, succinct result here. And once again, we're looking at that resolution parameter as our key parameter. Where remember, lowers fewer larger clusters, higher resolutions, more smaller clusters. And just a couple of other parameters we have in iterations. Just the number of iterations for that refinement step. It gets slower the higher, but the more it goes through, the better usually, but the default is usually pretty fine. And finally, its partition type is an extremely complicated parameter. And it has a lot of different partition types. These two happen to be the best for single cell RNA, but it has I forget how many are there, like six of them or so. And basically they differ in what quality function they optimize, right? And what null model they assume, how sensitive they are to cluster size, and how they treat that resolution parameter in the analysis. And the CPM is the default, but I actually found this RB configuration to give a better results in our data. So really you just need to try both of them and see what's better. And just be aware these different partition types can affect your results. And if you have, you can look more into them. They're a little bit complex to go over at this level. So let's look at our actual function here, because I'm once again I'm looping through the resolutions for you. But the function is Leighton find partition. You put in the cell graph, your partition type, like we talked about above, the resolution parameter, which is really your only parameter, your number of iterations if you want to change. And then basically we grab the membership once again to get our clusters. So let's run through the different resolution values here. And this is very interesting, I think, that the higher the resolution, the more clusters, right? The more clusters we're seeing, but we're seeing a lot of over-clustering because of that. So we need to kind of balance which one do we want between 8 and 9. It's kind of hard to say which one is better. This over-cluster a little more. Maybe this one's a little bit better, the 0.3 one, to kind of leave some of this. But then again, the 0.3 over-clusters that, so it's hard to say. You could go with 0.3 or 0.5 there. I went with 0.3 just for the sake of it, and I reran just the function here for you to be able to see it cleanly. And then off the object, I called the membership to get my labels, and I calculated my modularity score 0.77 as well as here. And then I went ahead and plotted again against the true cell types. And once again, you're seeing some over clustering here that you don't see there, over clustering there. You're not finding those, so it's not perfect, but it's finding them pretty well. And see, like once again, I mentioned it's finding things that look like clusters. It's not necessarily wrong. And the whole idea is later you come back and the cell types. And once you know the cell types, you can look in the clusters for the expression. The expression. You look for the expression and see if it matches the cell type, right? So that's where you're going to find this granular stuff. It's going to be really hard for an algorithm to be able to separate that out. But let's see. So, but yeah, so we got a pretty good result there on Leighton. And so what about the k-ing graph? Remember I told you could change that? Obviously, if you set up the graph a certain way, it's going to change the result. Well, so I looped through and just made the k's higher. And as the k's go higher, you find less clusters. They're smaller, right? Like we talked about. We're grabbing more k's all around us, right? Then we're gonna have less clusters. So that's what we see there. Be aware of that to affect your k value. So you got to kind of balance the cell graph and the resolution parameters. And once again, I showed you some stuff here where you can look at the membership, modularity, and grab some of the metrics there if you would like. All right, so we got through our graph-based models. Let's do our probabilistic model, which is kind of a cool model. I think that this Gaussian mixture model, which we're going to do soft clustering. So soft clustering instead of hard assignments like k equals 3. You got to be one cell. You're in cluster 1. That's it. Sorry, there's no probability. So you're just in the cluster. You're not. That's hard clustering. Soft clustering is every point, every cell has a probability to be in a cluster. So I have a certain probability of cluster 1, certain probability of cluster 2, 3, and so on, right? So this is a probabilistic clustering algorithm that assumes your data. So you give it the number of k values. It assumes your data comes from a mixture of a given set of normal Gaussian distributions, okay? And then we give it each sample a probability of belonging to each cluster. This is good for soft clustering, as we mentioned, for probabilities. It's good for capturing uncertainty between different clusters, and it's really good for very flexible cluster shapes, and it gives us a very strong statistical foundation for our answer. It uses Gaussian distributions, and you have to choose the k, just like times above. It's very sensitive initialization, so it's good to rerun it a bunch of times, and it's very related. It's related to k-means, which is actually k-means is a special case, a spherical version of equal size clusters of GMM. So I think that's kind of interesting. So how does GMM work? So just think about this. Imagine you're seeing clouds in the sky, right? And you're trying to cluster them out. Some are overlapping, some are clustered. Some are separated out as a cluster. How can we find those using GMM? Well, the first thing we do is we say, okay, I see four clouds, I think. I'm going to give you a k value, or here we call it a g value, of how many components we need to explain the data. So I'm saying, hey, I think it's 4, okay? So I'm going to choose my 4, and I go to all the centers, what I consider the centers, and I find the center, and I choose that as kind of basically, it's going to be referred to as the mean, but that's going to be the actual center. It's basically the center of the Gaussian distribution. The mean is basically the center of the Gaussian distribution. So we have a Gaussian distribution basically on each cluster. And it's centered it by the mean in the middle, and its shape is by the covariance, and the way it is connected, locally and globally is based on kind of the weights. So what we want to do is we want to guess basically these values, kind of initialize, guess the mean and the covariance, guess the center and the shape, and then basically based on our settings, calculate the probability, model basically the probability that each point belongs to each cloud, right? And we'll get a probability, and then we'll just keep adjusting the points which means update the center, update the shape, and so on, and the weights until we get the best result, right? Until we make a model that explains the data the best. So that's how it works. So basically, you find this probability, and then we maximize it. We maximize it by the log likelihood. So we be making changes till we have the best log likelihood of the data being, the model explaining the data, okay? And the key insight we talked about is these soft assignments, these probabilistic assignments. So our key parameter, 2 key parameters. One is the number of components, which they refer to as G, which is the number of Gaussian distributions we expect to see. It's just like how many Ks and K means. And then we have model names, which we can put in lots of different models to try out to see if they explain. And usually what you can do is just try out a bunch at the same time. And they're just kind of different in the way they handle just basically everything, the covariance, the shape, the orientation, things like that. So let's do a calculation of GMM. We use mclust here. We put in UMAP coordinates as our input reduction. and we're basically saying I want to try G from 1 to 15, and I'm going to try these models. So it's going to run through this whole thing and try out every possible combination and give us our answers. Then we just can plot this by what BIC, and we get this BIC, which is a measure of how well our models are explaining the data. And basically where the model stops, you go down, and that's your component that you're going to want to use, just your best component. And because remember, we're choosing all of them to see what's best. And basically, the higher this goes, MPlus is really weird. You want the lowest BIC, but for some reason, MPlus does it the reverse sign. So just to confuse things more, you want the lowest BIC, but in this plot with MPlus, you want the highest. Sorry. So you want the highest up there, the highest negative. The lowest negative is the highest, right? So anyway, you can just plot, you see the highest one is the VVV model with 13 components. So we're going to choose those for our model and go ahead and plot that back. This is just some kind of looking at the probabilities of some of the cells in each cluster. So that's what's cool, is every cell has basically an uncertainty value or probability of being in each cluster. So let's kind of look at the results here. The middle is those trues. The left is GMM. It's not doing too bad. Overclustered this, but it found some of these small guys. It separated out these guys, so that's good. Overclustered a bit here, but it's not, once again, not doing horrible. And here's what we really do is we can visualize the uncertainty here now. This is really cool. So we've kind of taken a measure. We've set a standard of uncertainty, and all the red cells here are ones that have high uncertainty. So these are cells, remember, that could possibly be in another cluster. Their probability isn't super high that it has to be there. And what's really fascinating to me is these areas are areas, the clusters, the algorithms have been missing a lot every step of the way. This area here, I mean, look, this area here, this green, is this thing is pretty much exactly this. This little tip here is this guy right here. These guys have been hard to find. It's right there. So a lot of these ones that have been hard to find have been these uncertain cells. So this kind of makes sense. So two things. One, they're kind of hard to find, which is difficult, but the other side of it is they're cool, right? They're probably different. Like these are all, I forget, these are all T cells, right? Well, these could be not necessarily uncertain, but just they have a lower probability because they're transitional, right? They could be kind of between different clusters, right? Between different states. So this is kind of a way that you possibly could find, transitional cells, and also outliers too. So that's, I think it's really cool about GMM. And, if you have over 90% probability, you're considered a very confident assignment. So really things under a max of 80% are kind of, for one cluster, is kind of what we're talking about uncertain. So, having this really cool posterior probability representing the uncertainty for each cell is just, I think, really cool. It's a really cool method. And here's just some ways of looking at some of these metrics, pulling out some of these results to kind of help you out there. All right, so let's go to our final type of clustering we're going to do today, this density-based clustering, which is a really, really cool base. I really love density-based clustering. It's really good for spatial data. And the idea is based on the density. Density is how close together, right? If things are closer together, they're probably more clusters. So we're going to measure the distance in a way and use that to find our clusters. So basically looking at how close points are packed. Are they sparse? Are they close back? And we're also going to try to look and look for noise, which is going to be really cool. So DB-Scan is really good at finding arbitrary shapes and nested values. So those little tiny little things are hard to find. DB-Scan is going to be really good at that stuff. And you don't have to name the number of clusters. It finds itself, and it's really good for outliers. So it's really good at finding outliers and noise. Often you will use DB-Scan only to find noise and then use something else later. So it's really great at that. It only has two parameters that are pretty simple. This epsilon I'll talk about in the middle, and then samples. And once again, you need to run a seed on it, just to be careful. Okay, so let's talk about how this works. So basically, let's just think about, and this analogy, a crowd at a festival, right? We're looking at different crowds. Different people are in different niches, right? People there's the goths over there the metal heads over there, whatever. People are kind of close together. So they're kind of a little bit dense. Those areas are denser, right? Because the people are more near each other, right? So we're already kind of seeing this spread, right? So what we do with dbScan is we go to one of those clusters, or what we assume to be one of those clusters, and we take a point. And then based on the epsilon value we've set, we take a radius around us. So let's say we take 10 meters as our epsilon value. So we draw a circle around us of 10 meters, and we count how many people are in that circle with us, right? And then what we're going to do is basically, based on a value we set, we're setting kind of a minimum points value as a parameter, okay? And if the number of people in that circle that I just drew is greater than that minimum points, then I consider that a core point, okay? If it's not, I consider a border point. If we still have points in there, but it's less than minimum points, it's a border points, right? If there are no points at all, then that's an outlier in that circle. So you're far away, right? So really just the more dense things are, the better chance you are of being a core point. So we find all those core points, right? So now we have all our core points, and basically we expand that radius for each of the points, and if other core points are within that radius or touch it, then they're assimilated basically. And then we just kind of move around the little dice and we assimilate all the little clusters, or the little core points until we can't do it anymore. Then we have a cluster, and then we move on to our next area. We do the same thing, and that's how we find our little clusters, right? And then our border points, we can either assign them as noise or not part of the cluster, or we can assign them as part of the cluster. Usually they are, because they're on the edges of clusters. They're normally assigned as default at least. And then that basically separates. Now we have our disconnect, where those core points didn't go any farther. Those are disconnections, and we have our clusters. So our key concepts, our parameters, are our epsilon value. That's that radius I talked about, right? The core points. Remember, if it's at least minimum points within that circle, it's a core point. Otherwise, it's a border point, noise point, neither, right? So that's how that works. And it uses a Euclidean distance to look at for that radius or whatever. We're basically so we don't have an objective function here. We just kind of enforce this density connectivity criterion, where 2 points belong to the same cluster only if there exists this chain of core points. Just like I mentioned, if the chain stops, then the cluster stops, and no one can be a part of it anymore, right? All right. So this key insight is this kind of local density perspective, right? Instead of assuming clusters look similar, we're looking for how much they are crowded, how much we are crowded together. And just the parameters, remember, if it's too small, we get too tiny clusters. If it's too large, we'll have everything smushed into one. If we have too small here, minimum points, then we'll have more clusters with more noise points. And if it's too large, we'll have fewer, denser clusters with more points. Unclassified as noise. If the other one's more points, more noise as clusters, right? So we need to be really careful with the minimum points to get really a strong evidence of our clusters. And the border points we talked about, do we assign them to cluster or not? I do, so I say true. All right, let's get our result now. It's pretty easy. We just run dbScan here on our UMAP coordinates. We put it in an epsilon value like we talked about, and our minimum points here. And based on these values here, we have dbScan equals 13 clusters, 22 noise points, which is 1% of the data was noise. And we can visualize that here. And we can see we have 12 clusters. The gray points are noise, so right there is noise. Right there is noise. You see, this did a pretty good job. What jumps out at me is it found this. No one's been able to find this, right? It kind of flipped it a little bit, but it almost got it. It grabbed this guy by itself, but it still kind of overclustered these guys. But that's kind of to be expected. But it's doing a pretty good job. One of the better jobs, along with Leighton so far, to get this. If you want to find optimal parameters, like what value should we choose for the epsilon? One thing we can do is we can make a kn distance plot here. So basically just throw in the UMAP coordinates, this kn dist function, and then we basically sort that and plot it. And we see here as the points sorted by distance get farther and farther away, and we increase epsilon values, we have this curve here that has this inflection point. And when you see this inflection point, that's kind of what you're looking for. And you kind of get the inflection point we're seeing here. This is by view here. I did this, our point, the 0.5. Where I use 0.7, that's 0.5. So let's do a grid search. We're going to try out different values of the EPS and min points and see the results. Here are results here. You can see, for example, with 0.5 epsilon, 20 points, we have 16 clusters, 113 noise points. You want to kind of avoid these because they're so high, right? And avoid like this guy because it's too low. So these are kind of low. So if I had to look at this just off my eye, I'd probably say the 0.520 is probably the best on that. So you kind of have to play with it a little bit. It's a little bit of an art form, but that's how you can kind of choose that. And here, once again, there's some of the metrics interpretations you can look at to get in more detail on that. So finally, our last method we're going to talk about today, HDB scan, which is basically a hierarchical density base. So it's adding a hierarchical instance to DB scan to improve on the critical problem of handling clusters with varying densities. So the big problem with DB scan is what if clusters are different densities? So think about how these clusters spread out, right? Those cancer cells spread out. Well, if things are really, remember when TC&E kind of spreads things out? Well, the cluster isn't dense, but it's still a cluster, right? So just because something dense are bigger out, that's just global and local structure. That doesn't mean the cluster doesn't exist, right? So DBScan could see a spread out guy and then think there's a lot of more clusters and not realize they're all part of one, right? Especially if there's a dense guy in one corner and a big guy in another corner. Different densities in the same data. That's what really makes DBScan, or really, it really hurts it in its ability to give you an optimal result. So basically, HDB scan is eliminating this EPS parameter. It's going to tune it, kind of auto-tune it itself, right? All we care about is just minimum points. We don't care about EPS anymore. It's going to be able to handle varying density well. It is going to look at the hierarchical structure. It's going to build actually a cluster hierarchy based on different density. It's going to check out the cluster stability and give you a really robust result that's less sensitive to the parameter choices like epsilon. So DBScan is extremely sensitive to that epsilon value, as you can expect. So another cool thing is DBScan returns you a tree at each density level. So you actually have a cool tree to look at. You could heat map it and look at the clusters. So it's really cool because that would be a really easy way to jump in and maybe like H cluster genes in that cluster and get some idea about the biological interpretability of the clusters, right? It basically automatically selects the best clusters, the best density threshold, and it's really good at still finding noise. It's just really better for biological data sets that often have different densities and becoming one of the standards, especially in spatial single cell analysis. And so how does this work here? So it's basically the same thing as DBScan. There's only one difference. Just imagine, super simple, it's doing DBScan at every epsilon value, right? So imagine you're looking at, once again, these festival crowds, right? Or let's look at, go back to the New York setting. I think the New York cities work well. So if you zoom really, really far into Manhattan, you might assume Manhattan's is part of your cluster. And you look farther away, you see like Brooklyn, you're like, that's not part of the cluster. That's far away. So you're zoomed in on a really low density, right? And if you did your calculations there, you would definitely cluster out Brooklyn, things like that, the different areas. Well, but what if we're really looking for New York? Well, if we zoom out and look up in space and look down, or space, just even up high a little bit, right? And we look down, now it's much more dense, right? And the entire city of New York looks like a cluster itself. And Philadelphia looks like another cluster far away, or whatever, you know what I mean? Hoboken, New York. So you can see how the different ways you look at the density of a cluster can really affect your result. And imagine you're looking at different size cities around you. The zoom would change the density that you're actually viewing, right? So HDB scan is basically doing its calculation by very similar the same way, but doing it going across. It's doing it in a density aware approach. When it calculates its distance as a density aware approach that lends itself to kind of try out or assumed it's looking at all different densities. And what's cool is it builds this minimum spanning tree, which is just a tree spanning all the data, and a hierarchical, looking tree, like we looked at with heat maps and HClust. But it builds this tree for every single density level it's looking at, right? And it basically tracks the clusters across these density levels. And if a cluster stays stable or stays intact across most of the densities, then it's kept as a stable cluster, right? Because now we know it fits all the different density levels of the cluster. So that's the difference. It's basically dbScan at different densities, where you can build a tree and look at cluster stability, right? So that's kind of how HDBScan works there. So let's look at it, and it's just maximizing this cluster stability, this persistence of clusters across density levels. So we talked about this. We don't have to use an EPS parameter. We have just our minimum points parameter. So remember, it's the minimum points to form a cluster. So I guess it's a little bit different than the epsilon version of the min points, but it's just basically the minimum points we need to actually feel like a cluster is actually real. So obviously the larger values, you have larger clusters, right? Okay, so let's run HDBScan at some different parameters. It's our only parameter, right? So let's just try different ones. It's just HDBScan. We're putting in the UMAP embedding, looking at the points. What do we get here, right? Well, what we're seeing here is as minimum points goes higher, we're obviously, as expected, we're seeing more larger clusters. You see the minimum points equals 10. We see a lot of over-clustering here. We're not seeing that as they get bigger, but we're also losing some of the fine local structure as well too. But it's doing a pretty good job, I think, of finding. I like 20 because it kind of started finding little things here, even though it makes other mistakes. But I think 20 looked pretty well, pretty good. And we can kind of look at just kind of a summary of that. Here's the number of clusters found, the number of noise points. And I'm saying I think 20 is kind of a good balance of that. You could also look at the cluster stability scores by looking at the cluster scores here off the object. And here's for minimum points equals 20, it's 231. For 30, it's 193. So 231 is higher. I feel pretty good about that being the best one. So we're going to go with that and run it again with the best parameter. Minimum points equals 20. And just take a look at the result here. And like we saw ahead, it looks pretty good. So the gray points are noise here. And, it over-clustered, of course, a little bit like all of them are, but it's doing a pretty good job of finding the clusters. We just might need to merge them a little bit or change things up a little bit, but it's doing a pretty good job. And once again, you can look at this to kind of get look at the membership, outlier scores, things like that. So, what's really important about dbScan, it's really hard to see here because there's not too much noise, but HDBScan is really good at finding noise. Kind of like GMM is good at finding uncertainty. So, there's often times where HDBScan will be used first on the data, and you will find the noise points, remove them, and then you'll run something like Leighton after that on it. That's perfectly okay. It's something that's very common to be done. So just to know, HDBScan is really good at finding those outliers, those noise clusters, right? So we're going to compile all the results. Basically, you see all of our memberships and cluster relationships there. And we're going to try out some different parameters. It's a test. We're using the ARI, this adjusted RAND index, which is kind of you're comparing the labels without having the labels. We're going to calculate the silhouette scores, cluster stability, and we have a few more: Davies Bolden and Kalinske-Harabaz done, and Peterson Gamma. Just some different ones I wanted to throw in there. And I'm just going to jump ahead to the result here. I have it all summarized in graphs, easier to see. One thing that jumps out right away is that the Kalinske-Harabaz and Dunn aren't good for single cell data. And you can see they're not really doing a very good job here. And I just wanted to show you how that not all metrics are perfect. And while these work good on bulk data, they're not so great on single cell. So let's look at these four here. They're all higher better, except that Davis Bolden's lower is better. And we look here, we're seeing Leighton and HDBScan are doing pretty good. Once again, HDBScan's doing great. Over here, Leighton's doing good. So, we're really kind of seeing kind of a Leighton, dbScan, HDBScan thing that's working the best here. It seems to be. While all these different metrics are different scales, so I'm basically going to normalize them and create a heat map, just showing you, one's the best, zero's the worst, just kind of showing you a normalized score of how well these methods are working across these metrics. So you can see things like HTTP scan, got a 1 here, 0.97 here. Leighton got 2 1s. HTTP scan, DB scan, I got a couple of good ones. GMM one of them, right? But I'm really seeing Leighton has almost 2 1s, and HTTP scan has almost 2 1s. And Leighton Leighton didn't just do so well on silhouette. Had a problem. So in comparison, so that's why it's a little bit lower. But I think if you look at all of them together and we average them together, the HTTP scan is the winner here on the average, and then it kind of matters. Leighton's a close second there. So really, HTTP scan and Leighton, as expected, outperformed the other guys. And I also take a caveat too that we didn't normally, you would, for each one of these methods you would spend like days, weeks, calibrating these parameters and going back and forth in biology. This is just a first pass through it to get a general idea of what it looks like and how you understand how these methods work. So just keep that in mind. If you look at the best method, Leighton was the best, our true labels, HTTP scans best silhouette score, GMM best, the Davies-Bolden, Leighton the best Pearson gamma as well. But once again, we're seeing Leighton HTTP scan on the top. And here's kind of an interpretation guide. I'm going to let you guys go through this. It just kind of gives you an idea of, the ranges in these different guys and like what does it really mean? How much higher does it really matter or how much lower does it really matter to interpret the results? Just kind of interpreting the results. We have an ARI with Leighton of 0.57. With HTTP scan of 0.57, 0.606 with Leighton. This one's the best. You may think this is bad, but remember, we're capturing this is looking at the label, how well we're capturing the labels, not how well we're capturing the clusters. So labels are going to be more resolute, have a higher, have a much more distinct information. So it's obviously not going to be able to capture all that. And actually, this is actually a pretty good first pass result. So it actually looks pretty good. A lot of these boundaries on these clusters differ. And cell states can lie in a continuum. They're not necessarily in one spot, right? So, that's why, you don't get a perfect result for cell types, or we're looking at clusters. So I feel good about it. We did a good job. And here's just some kind of interpretation, if you want to take a look at it, of the results, and kind of a framework here. If you want to look at kind of a flow chart, if you want to use spatial data, DB scan, HTTP scan is great. If you want to do bulk RNA seq, grab 5 to 15 dimensions of your PCA, make a UMAP if you want. Use hierarchical k-means or GMM if you want, soft clustering. For single cell data, you go a little bit higher on the PCA dimensions. Use your PCA for your UMAP and use something like Leighton or Louvain. And if you have special cases, use something like HTTP scan to find noise or outliers, GMM for uncertainty, and you can test out if you want what embedding do you want to use. PCA UMAP, you want to use the UMAP version of PCA and UMAP, a double one, right? Just more summary of some of the methods. I kind of tried to provide you guys with a lot of little metrics and things to look at because we have so much information in this. So the last thing I want to do is just kind of run you through a really quick Seurat tutorial for single cell data. I'm sure you guys have heard of Seurat. 10x. Uses this. This probably was dealt by a private lab, but 10x works with them, and that's what people use for the most part for 10x data for their pipeline. But you don't have to use it for single cell data. You don't have to use it for 10x data. You can use it for anything. So basically, you can make your own Seurat object, and it kind of mimics the one they make, and then you can use all the same functions. So all I did was I took my count subset, and it was the final subset before we did our PCA and that stuff. So it's kind of our normalized and we picked out our 2,000 cells, and then we have our metadata, which just gives you the cell types, and basically we use that to create our Seurat object, and then we run through our workflow here. It's very similar to what we did. We do our normalized data function, find variable features, 2,000 genes, right? Find the most highly variable genes, scale the data, run PCA, do an elbow plot, you know what I mean here. Find the neighbors, which means make the K&N graph with 25 dimensions, just like us. K and N of 40. And you can find clusters, using you can add the resolution, things like that. The algorithm number, if you put 1 in, it's Leighton, 4 in, it's Leighton. And you can run your UMAP and TSNE and visualize your result. And just kind of just running through that really quick with that SC subset, here's kind of our results were. Here's the true cell types, and here is our, on the left, and this is actually the TSNE version of it, just for fun. And, it does a pretty good job of finding things. It overclusters here a little bit, and it also doesn't find the finer grain here. So it's very similar to some of our results. These parameters were very similar to ours, except but for some reason they got not for some reason, they got a little bit less clusters just because the pipeline's not exactly the same. There's a little bit of difference in the way they do things like normalization, things like that. But I just wanted to show you this pipeline is very similar to the one we did and much simpler to use for a beginner. So it's worth a try to play on it. And these things are very easy to use. Very, very easy to get a quick result in Seurat. It's very hard to get a final result. So don't feel like the first result has to be good, and also don't celebrate the first result because it likely needs to be changed. And if you look at our result, if you do the ARI between the Seurat version and our Leighton version, which is they're both Leighton, we get almost a 90% agreement. So you can see that the protocols are pretty similar. And the Seurat agreement was 0.63, which is a little bit better than our best result with HDB scan, or Leighton, but very similar, right? Just kind of a bonus. Remember I did that Jack Straw earlier I saw, just really quick, I'll show you. I ran this Jack Straw and I scored it, and it's kind of their statistical way in Seurat of finding the right dimensions to keep. And here I kind of just showed you here, you want to check it out, how to calculate the best value. And we basically chose the best dimensions to use, and it's 25. So I just wanted to show you that it's exactly the same thing as we got for Horn's parallel analysis. So that's nice to know that we got similar values, and we know our method's working well. And I just have a couple practice exercises for you that I showed you really quick. I downloaded this barren pancreas data set from the same experiment hub, and I created this Seurat object off the counts, and I actually ran this Seurat pipeline. You can see how simple this pipeline is. Pretty amazing, right? It's just straight up, just really easy. You can just pipe it all in. All you got to do is just make the object. All you need is the counts and the count data. All you need is the counts, the expression data, and the cell types, and make the object, and just throw it in right there. Bam, you have your answer. Remember, it's not the right answer; it's a quick answer. But you can. There's nothing wrong with playing around with this and adjusting those to get a good result later. And here's kind of the result they gave, their additional result for Seurat. For that pancreatitis data set. One more thing you can do I want to talk about is consensus clustering. So if none of your models give a good result, a lot of times you want to combine models. That's done a lot of machine learning. So if we combine several different models, maybe we'll get a better result. So basically, if you want to check this out, I basically have run Leighton, GMM, and HDB scan, and basically combine them here together as consensus here. And you can kind of check out how I have done that data. I'll leave that for you. And finally, we get an ARI of 0.57, which is pretty good, pretty much up there what we've been getting. Not better, but still there. And you can try different combinations to see what you get, but often consensus clustering can give you a better result. And our final exercise, I wanted to talk a little bit about finding rare cell types and transitional states. We kind of mentioned this earlier with HDB scan and GMM. So if you set HDB scan to really small, like 5, you're going to have very, very small clusters, right? And that's a really good possibility of finding a rare cell type. And I did this here. I set this as 5, and I checked the cluster sizes, and I just found clusters that contain less than 2% of these cells. So I found 11 rare clusters here that had less than 2% of the cells, right? And we checked those out. They are very similar to the uncertainty values, I think, with GMM, and they show possible outliers as well, too. So these are possible rare cell populations. That's pretty cool. And it actually said those were T cells. That's for the next one, sorry. The rarest of all was the T cells. Okay, that's what I was saying. But anyway, that's how you get those populations. And you look at GMM, we'll do the same GMM, but this time what we'll do is we'll find all of our uncertainties, right? All of our posterior, our probabilities. But this time we're going to see, okay, is there a cell that has over a 15% probability of also being in another cluster? So it has over 80% of being in ours. Does it have over 15% of being in somewhere else? So I'm going to consider those as being kind of transitional. They could be in either cluster. There's somewhere between possible, right? They could be a transitional state or the same cell or a different cell state of the same cell type, right? And I found just 6 there. You can obviously adjust that percentage to higher, or I mean a lower to have more to get less resolution. But this is a very high resolution here, and I basically just got these tiny cells here. So these could be transitional or different cell states of T cells. And you can see how we only found a few, but you can see how this could be a very interesting method of way of finding these things. So just a summary of week 3. We talked about dimensionality reduction. We really want to reduce dimensions before clustering for the most part. PCA has that kind of initial reduction, but you can also add PCA into UMAP to get even a nonlinear, a stronger nonlinear, even based on PCA. And you can visualize it on UMAP. That's really the best way to do it, I think, for the most part. We did graph-based clustering, talked about that, which is really good for single cell data. It scales well. Leighton and Leighton are very popular methods that are often used. We talked about GMM. That's when you really want to find uncertainty in soft assignments, maybe to identify transitional states or just know the uncertainty of different clusters. And then we have our density-based methods, which is really good for outliers, finding noise and spatial patterns, nested values. And here's kind of your idea of what you're looking for. You want cell types, probably graph-based. Transitions, GMM's good. Outliers, HTB scan's great. Quick look, k-means. One I forgot here, hclust for looking at clustering genes, I think, within clusters. And here's kind of just a flow chart guide of where do you want to go if you're trying to find different things. Just more things I'm trying to provide you guys so you can get a look at things, so you don't have to go hunt down quick guides. I put them all here. So here's one for PCA, here's one for dimension reduction, here's one for clustering, just kind of showing you some overview. Here's some quick one-line snippets of these things that might have got lost along the way. And that's pretty much it. So next week, we're going to be talking about prediction modeling, which I'm really excited about. We're going to be doing continuous classification, how to set up models, split your data sets, do cross-validation. We'll talk about regularization and advanced regression topics like lasso, ridge regression, and we'll also look at distance methods and tree-based classifications, really more continuous classifications, or this is not really not a classification, right? It's more of a prediction. But you can also look at I provided the homework assignment this week. It's a really, really good homework. I think you guys can learn a lot from it. I basically analyzed 2 different pancreatic data sets, and I went through the whole deal with problem number 1, looked at 4 different methods. 2, kind of looked at the metrics and the biological validation of those. I even looked at actual real genes and everything. And then for the problem number 3, I compared different processing methods on the barren pancreas data, and you guys can have those. You can always use those later, just copy them. And then I kind of just talked about some stability analysis. Here's some online tutorials, things you could look at. I particularly like this StatQuest guy, StatQuest with John Starmer. There's a lot of cool stuff there that are really quick videos that are also kind of funny. And that concludes our 3rd week here of the R machine learning workshop. And I'm just really excited to have you guys here, and I look forward to our next meeting. Thank you.